Calculation of system noise temperature. So if we have a system like this, how we can calculate the system noise temperature? So this is the simplified communication receiver with RF amplifier and single frequency conversion from its RF input to the IF output. Well, this is the form used for all radio receivers. This is actually heterodyne tape receiver with few exceptions, and this is called the super heterodyne receiver. The super heterodyne receiver has three main subsystems. One is the front end. So this is the front end. It is basically the RF amplifier, mixer and local oscillator, an IF stage, IF amplifier, and a demodulator and baseband section. That is not shown here, but it is there. The RF amplifier in a satellite communications receiver must generate as little noise as possible, so it is called a low noise amplifier or LNA. Okay. The mixer and local oscillator form a frequency conversion stage, this one, that down converts the RF signal to a fixed intermediate frequency, which is called the IF, where the signal can be amplified and filtered accurately. And IF is chosen in such a way the amount of noise or available noise power becomes lesser. In RF's range, the amount of noise is higher, but if we down convert it into IF, the amount of noise contribution would be lesser. That is why we are this conversion is done from RF to IF. This conversion is done to minimize the noise. Now, if we draw the equivalent circuit of the previous one, then we can draw it in this way. The noisy device in the receiver are replaced by equivalent noiseless block with the same gain and noise generators at the input to each block such that the block produces the same noise at its output as the device it replaces. So we had RF amplifier, right? We have RF amplifier. So RF amplifier is replaced by a gain box, right? Gain box which is noiseless along with a noise source at the input, right? And input noise is represented in terms of T in. Similarly, this mixer stage is replaced by a noiseless mixer along with a noise source Tm. For IF amplifier, it is equivalent form is a noiseless IF amplifier with gain GIF along with a noise source TIF. Okay, so in this way we have divided the LNA part. This is the low noise amplifier part, this is the mixer part, and this is the IF part, right? So we basically what we are doing, we are actually dividing the functionality of each block into two parts. One is the gain part, another is the noise part. Noise is represented in terms of a noise source. Okay, the entire receiver is then reduced to a single equivalent noiseless block with the same end-to-end gain as the actual receiver and a single noise source at its input with temperature Tn. The total noise power at the output of IF amplifier of the receiver is given as Pn equal to, so if we add all these noise components, it becomes GIF into KTIF into Bn due to the IF, right? Due to the mixer, so noise generated by mixer is Tm, right? So corresponding noise power is gm ktm into bn, that is going through this gain part, if gain. So it will be multiplied by gif, right? And this noise, what is the input to this noise? Tin was there, at the same time trf was there, right? So trf plus tin, this is the noise associated with this portion, right? So overall noise will be grf ktbn into trf plus tin, right? That noise is going through both mixer as well as if. So that will be multiplied by gm and gif. So gif and gm is multiplied. So this is the total uh, noise contribution. Okay. So that can also be written in slightly different way. You just take the GIF, GM, RF, GRF common, and uh, it becomes GIF, GM, GRF, KBN, and inside the bracket you have TRF plus Tin plus TM by GRF plus TIF by GRF, GM, right? So if we have a single source of noise, that means the three stages, RF stage, mixer stage, and the IF stage. All these three stages are now combined to form a single stage, right? And its equivalent form will be a noiseless receiver with this gain along with a noise source. Okay, this is the noise source of this source is due to the uh, equivalent noise source. Its temperature is say Ts, noise temperature. Mind it, noise temperature, not the actual. So for this case, the noise power at the output will be grf gm into gif, total gain, multiplied by kts into bn, right? So the noise power at the output of noise model for this figure will be the same as the noise power at the output of the noise model in the previous situation, the original equivalent circuit. So equating those two equations, we have ktsbn equal to kbn into tin plus trf plus tm by gif that we have discussed in previous slide, right? So this kbn may be cancelled out in both the sides. So equivalent noise source with a noise temperature of Ts can be written as Tin plus Trf plus Tm by Grf plus Tif by Gm into Grf, right? Succeeding stages, we have considered only 3 stages, but other stages are there, right? Demodulator is there, filters are there. Those stages, succeeding stages of the receiver contributes less and less noise to the total system noise temperature. Why? Look at this expression. Forget about this T in, because T in is not in our hand. It is the input noise, right? So if input noise is higher, T in will be higher. If the input noise is lesser, T in will be lesser. That is not in our hand. But observe this TRF. What is TRF? TRF was the noise temperature of the RF stage. That is the LNA, right? LNA. So instead of LNA, if we have used some common kind of amplifiers, then corresponding to those that amplifier, the value of TRF would be higher, right? So if we use LNA, the amount of noise contribution will be lesser. So for LNA, TRF will be lesser, right? See, there is no denominator term here. So if this term is higher, then overall noise temperature would be higher. Get it? But look at the second stage, mixer stage. This is the noise contribution from the mixer stage divided by GRF. What is GRF? It is the gain of the RF stage, right? So since this GRF is in the denominator, so more the value of GRF, lesser will be the overall contribution for the mixer, right? So if GRF is instead of 10, if we take GRF as 100, okay, or 1000, then the corresponding contribution Tm by 10, it will be Tm by 100 or Tm by 1000. So contribution of this term will be much lesser if we can increase the value of GRF, right? And as far IF is concerned, the third term, right? IF was in the third position, so third stage. So TIF divided by GM multiplied by GRF, okay? So its contribution is even lesser because along with GRF, we have GM term. So its contribution is even lesser. So if IF amplifier noise contribution, suppose it is very high, right? Suppose TIF is very high, but this TIF is actually divided by GM and GRF. So if we can keep GRF very high, then the overall contribution of this term will be negligibly small, right? Similarly, for subsequent, if we analyze for subsequent stages, then you will see that the fourth stage will have a corresponding noise temperature divided by GM/GRF multiplied by the gain of that stage. So its contribution will be even lesser. Get it? So what we saw is that the first stage plays the most important role in noise contribution. Get it? Because TRF is there. So if TRF, that is the noise contribution of the first stage, so we have to keep the first stage as low as possible. Noise contribution should be as low as possible. At the same time, this GRF, that is the gain of the first stage, it must be as high as possible. So if we maintain this this idea in our design, that GRF must be very high, TRF must be very low, then the overall contribution of noise for that particular receiver would be minimum. Okay, so first stage of the receiver plays a very important role, crucial role in receiver design. Okay, the subsequent stages contributes lesser and lesser as far noise is concerned.